general relativity step by step. Last time I derived the covariant vector derivative. So we have a vector with a contravariant index, and I was differentiating it covariantly with respect to a index j, and that is equal to di vi by di xj plus Christoffel symbol, i's on the top. No, it isn't. It's contracted with an m. There's an m. I's on the top, and what have we got left? A j. Well, that's great. And so we've got the two components here. This one tells us how quickly v itself is changing, or the components of v at least. And this one tells us how quickly the basis vectors are changing, because we know that ijk equals, get this right, di ej by di xk equals that. It's always a little bit tricky to get these things exactly right. Have I got that right? Yeah, the I is contracted on the left. These two i's are contracted. J and k are free, which is this j and this k here. Okay, so now what I'm going to do, so this is quite a useful thing. We're going to need this over and over again when we start talking about physics, when we get back to physics. What I want to do now is to think about a vector. Let's call it W, actually. Do that again. W with a covariant index, and I want to differentiate that covariantly. So I want to differentiate it, and I want this to be a tensor. Want this to be a tensor. And this is one of these things where there's 5 or 6 different methods to try. You can try raising and lowering indices, you can try fooling around with all sorts of other things. But there's one way that works. And if you know that, everything's easy, and if you don't, it's impossible. So what I want to do is to consider this. I'm going to consider vi, that's this vector here, that's that vector there, but I'm going to contract it with wi and take a covariant derivative with respect to index j. So this thing here is a scalar. So what I'm going to do is I'm going to fool around with this scalar thing and mess around with it in different ways. So it's going to be equal, because it's a scalar, there's no Christoffel symbol here. So I can just consider di xj vi wi. And then I can use the product rule to say that, let's get this right, I've got u v dash equals u dash v plus u v dash. So that equals, I might mess around with the coordinate systems, but it's di vi by di xj wi plus vi. Notice how the product rule still works even through a summation. Everything's finite, so everything's going to work nicely. Di wi, but it's as well to say this kind of thing, di xj. Now what I'm going to do is I'm going to expand this guy here. No, I'm not. Yeah, what I'm going to do is expand this guy here in terms of its covariant derivatives. So I'm just going to expand it in a slightly different way. I'm going to say it's vi semicolon j, and I know that, times wi, plus vi times wi semicolon j, and I don't know that. And that equals di vi di xj wi plus vi di wi by di xj. Okay, so let's just expand this guy. Expand, and that's wi times di vi by di xj plus No, that is an I, because the free term is the I, and I've got a J down there and a K which is contracted on the K. That's right. Plus VI WI semicolon J equals di VI di X J WI plus VI di WI by di X J. Getting a bit of a mouthful. Oops. Never mind. Let's do some cancelling here. What can cancel? What can cancel? I'll cancel in red, just because I can. That cancels with that. I think that's all I can do, isn't it? Okay, so I'll go back to black. And remember, we're trying to identify this thing here. So what we now have is, oops, VI WI semicolon J, covariant derivative, equals VI, this term here, di WI by di X J minus WI Christoffel symbol I J K V K. Where this is summed over i's. What I want to do is to factorize with respect to VI. So I'm going to rewrite this. I'm going to say it's equal, VI equals WI semicolon J, VI di WI by di X J minus WK KJ I VI. That's just relabeling of indices. I'm not doing anything clever there. So now this tells me that VI, and I'm going to bring everything over to the left hand side, WI semicolon J minus di WI, I'm sorry, di XJ, that's this term here, plus WK Christoffel symbol KJI equals 0. There we are. So what that tells me, that's for any vectors WI and VI, or vectors with any components VI. So this thing here must be 0, because I've got the dot products of something with this thing is always 0. This thing can be anything I like. So this thing here in the square brackets must be equal to 0. So that tells me that WI semicolon J equals di W. Oh, I've got a superscript where it should be a subscript. That should be no, it should be an I. See, I copied it down wrongly from there. WI by di XJ minus WK Christoffel symbol K. I may as well put it in alphabetical order like that. Okay, and so this is the rule for covariant derivatives of a vector with covariant components. Okay, and after a while you get used to this. That's a minus. Compare, I guess the word is CF. I'm not sure what that stands for. CF, some Latin thing. Let's take VI semicolon J, which equals di VI by di XJ plus the contracted Christoffel symbol. So it's W, no, it's not a W, it's a V. But because this is upstairs, it needs to contract on an upstairs index, which I'm just going to call K. That I and J are down there. No, they're not. that k contracts with that k down there. That free index I is this one here. That j downstairs is that one down there. Okay? So we've got basically the same thing. It's slightly different in terms of contraction because we've got a downstairs and an upstairs and an upstairs and a downstairs. But the crucial thing to remember is that when you are differentiating something with a subscript, it's got a minus, and a superscript has got a plus. All right, I'm going to stop there. This is longer than I intended.